Okay, so we're going to take this information, we're going to go ahead and do a couple review type problems, reviewing some of what we do, and then add a couple new ideas for what we're doing for topic 3. So the first thing I want to make sure we point out is that when you have problems that involve square roots or complex numbers, they come in conjugates. So if we have a plus the square root of d as a solution, then also if that is a root, then also a minus the square root of d is a root. They have to both be. So notice that conjugate idea that if you have a plus for one, you have to have a minus for the other. They always come in pairs. Well, that also works for complex numbers. If a plus bi is a root, then a minus bi is a root. Complex numbers come in pairs when there's solutions to polynomial equations. Now, just a little insight about the graphs of these. When we have the roots, these are going to be ones that actually cross the x-axis at decimal values that aren't nice, neat fractions. So they will cross the axis. These two, what happens is if you have a graph that, if you're drawing a graph, and remember we have the graph go up through an axis and come back down through the axis. If you have something that goes through the axis and then doesn't quite come back to the axis, so it would look something like this, where it goes through, that's a real root. But let's say then the graph goes like this, and it goes back up, where it looks like it wants to go back down through the axis again. It doesn't, that's going to be an imaginary root. That's going to have a complex number root. And that's why it comes in pairs, because there's symmetry to it, where it has to go down and then come back up. So that's where you will see this, is when a graph kind of does a little bit of a minimum or a maximum that never goes back and hits the axis. All right, so as an example, if I tell you, if I give to you that 2 minus 3i is a root, you immediately can conclude that 2 plus 3i is a root. Okay, they have to come in pairs of complex numbers. All right, rational root theorem. This will hopefully just give you some insights. This is not something you necessarily have to use, but it will give you insights about what the roots will look like. This is when it does cross the axis and we're looking at fractional values for the roots. Okay, rational root theorems are the basic theorem. The theorem says roots to polynomial equations are in the form of P over Q when they are rational, okay? Now here's the details of it. When where P P is a factor of the constant, is a factor and Q is a factor of the leading coefficient. Right, that's a lot of words, but basically what it means is if I've got a polynomial, here's an example, okay, example for us. If we have a polynomial equation where 0 equals 6x cubed minus 23x squared plus 15x and then plus 14. Now, there are a lot of factors of 14 and 1, 7 and 2, when we put them over the factors of 6. So 14 and 6, I'm not worried about these other ones right now. Just 14, the factors are 14, 1, 7, 2, and they're negatives, right? And then the factors of 6 are 2 and 3, 6 and 1, and they're negatives. The only possible rational answers for this could be the factors of the 14 over the factors of the 6. Okay, the way we factor, that's the only way that could be a possibility. Now, not all of those are factors, but those are the only possibilities. Let me show you what I mean by this. This factors into, if we were to factor it, we get x minus 2 times 2x plus 1 times 3x minus 7. So equal to 0 here. Notice the answer to this is 2, right? Well, that would be just 2 over 1. So that's what it works out to be. The answer to this one is negative 1/2. Negative 1 is a factor of that, 2 is a factor of that. And the answer to this one is 7 over 3, if I were to solve it. Factor of, the 7 is a factor of this, and the 3 is a factor of that. The only possible rational answers for these come from that. Now, if we have irrational answers or complex answers, it won't come from those. But it just gives you some insight about what those numbers are. All right, and lastly here, notice that I just put up a reminder of what some of the rules are for our exponents, just to remind you to look those up because and review over them, because sometimes people forget like what the negative exponent is, or they forget to bring that factor here when it's on the outside, bringing it into everything on the inside and multiplying.